Another example. And again, remember, with each example, we add just another layer of complexity to it so we can build into what we're doing. Now, just because it's a little bit more complex doesn't mean you can't do it. You can do it. So f of x equals 3x squared over x squared minus 4. First, check for some symmetry. Evaluate the function at negative x. What do you notice? My result is what I originally started with, so there is symmetry with the y-axis. File that away. Step 2, look for its y-intercept. Where's this value equal to 0 at? So 3 times 0, that looks like it just crashes down to 0 over negative 4, which is equals 0. So I do have a y-intercept at the point 0, 0. That's my step 2. Step 3, looking for the x-intercepts. So that's where the numerator, 3x squared, is set equal to 0. And that occurs at x equals 0. See, little steps aren't that difficult to do if you just do little steps at a time. Vertical asymptotes, where is the denominator equal to 0 at? Factor that. That's an x plus a 2 times an x minus a 2. So I have vertical asymptotes at the lines x equals 2 and x equals negative 2. And lastly, are there any horizontal asymptotes? Okay, notice the degree of the numerator, the highest degree of the numerator is a 2. The highest degree of the denominator likewise is 2. So we compare the ratio of the coefficients of those degrees, which is a 3 over a 1, which is a 3. So that tells me I have a horizontal asymptote at the line y equals 3. So with all that information, let's just start to build what we know. First thing tells me I have symmetry with the y-axis. Good to know. I have the point 0 and 0. Check. I also have the point 0 and 0 for, that was my y-intercept and my x-intercept. All right. Second one is I have vertical asymptotes. Yes, I do. I have vertical asymptotes at negative 2 and positive 2. Nice and slow. Easy does it. Horizontal asymptotes. I have a horizontal asymptote at line y equals 3. So what do we have involved here? Have all my asymptotes in place. I have one point on there for sure that I know. So we can start to look at some idea. I know right now what happens on the interval between, 2 and negative 2 and 2. How can I draw a graph that's bounded by these two vertical asymptotes, this horizontal asymptote, and it has to go through that point? The only possible way that could work out is if my line or my graph fits in that spot right there. No other way I could draw a graph that's bounded by these vertical asymptotes and goes to that point. So I had that in mind. Now let's just choose a test point. Let's see what happens over here at 3. So let's evaluate at f of 3. Because I'm not sure if my graph is above or below. F of 3 equals 3 times 3 squared, all over 3 squared minus 4. 3 squared 9, that's 27, divided by 9 minus 4, which is a 5, roughly equals some number greater than 5, which is above there. So that tells me then that this part of the graph fits in that process. It's bounded again by two asymptotes. No other way I could put that graph in there than in an orientation like that. The only thing might change is that maybe it's, down a little bit closer like that, or maybe it's a little bit broader. But for now, I'm more curious that that's the location of it, and then we can do some particular test points and some very accurate graph paper later if we want to know exactly where that bend is at. Now, do I have to do a test point over here? No. If you remembered our first step, there was symmetry about the y-axis. I know that I have a reflection, so my other graph is on that side. And there I had the full function, the full rational function, 3x squared over x squared minus 4. We were able to graph it. That feels awfully doggone cool.